Welcome back, ladies and gentlemen. What we're doing in this video is checking out how we might model motion of an object by looking at a different kind of graph, this time a velocity time graph. You'll hear me say VT graph as well. So let's check out a situation. We might have knowledge of an object's motion and specifically its initial velocity. So I can mark that right there as initial velocity. Let me use blue, it'll stand out pretty well. So since this is velocity on the vertical axis, not position, I'm not going to mark this with the symbol X. I'm going to mark this with the symbol V. And since it is the initial, I use a subscript I. And over here, that would be the final velocity. Whatever that value is right there, this is the final. I'll put a VF right there. Hopefully that's visible. Now, if I have knowledge of the initial velocity and the final velocity, but I don't know anything else, well, what I might be able to do is actually assume that it is uniformly accelerated motion. Because if it is uniformly accelerated motion, I'm able to connect those with a line, make it linear on the graph, and then we can do a few things with it. Now, if it's not uniformly accelerated motion, if it's weird and changing, I wouldn't generally want to connect it with a straight line. But if I have no other knowledge of what is really happening, I'm allowed to do this. Now, this is interesting though, because we have a linear graph. And anytime we have a linear graph, of course, we can talk about the slope of that graph. So, talking about the slope is always rise divided by run, as you'll recall. And well, in this case, what is our rise? Our rise is well, it's always the change in the values that are on the vertical axis right here. So what's on our vertical axis? Velocity. So we're talking about change in velocity. What I'm going to write here for the rise is delta V, change in velocity. For the run, well, it's the change that's on the horizontal axis. In this case, that is time. So I'll put a delta T. This might look a little familiar to you. We've already seen this before. If you look at your notes regarding accelerated motion, you should recognize this as being equal to the acceleration, acceleration of the object. Technically, this is average acceleration. Technically. But for uniformly accelerated motion, for UAM, the average acceleration is the same as the acceleration at any point along the motion. So, and that's what we study most is UAM. And so I'll probably be dropping that AVE subscript and just write an A for acceleration. There are situations where maybe that's not advisable, but let's not worry about that at the moment. We're going to be okay. So what does this tell us? Well, we have this equation where we use the slope of a line on a graph to be able to tell us the acceleration of the object. That's pretty darn cool. This is an equation you already have. That's supposed to be an A right there for average. Average acceleration is equal to the change in velocity divided by the time interval. There's another way of saying this. You could say that the average acceleration is the rate of change of the velocity. It's how quickly the velocity changes. So think about this. This is kind of cool, a little bit deep and not obvious at first. But what's changing? Look at this graph and ask yourself, what is changing? Well, time is changing. Time is moving forward, and time is changing. It looks like velocity is changing. We have an initial and we have a different final velocity. So velocity is changing. But there's more than that. So what else is changing? Isn't the object's position changing? Well, because it's moving, it has a velocity of some kind. Therefore, it's moving. Therefore, its position is also changing. Pretty cool. And as its position changes, its speed is changing along the way. All right, so now in this first graph, we definitely have what you can call uniformly accelerated motion, UAM. The change in velocity is smooth and continuous. Velocity is changing. It was here. Now it's up here at the end. but that change is smooth and continuous. That qualifies as uniformly accelerated motion. Let's look at another one. So check this one out. If we happen to know the initial velocity, maybe it's way up here at that value, and the final velocity sometime later is way down here at that value, maybe it's 0. Well, if we are dealing with uniformly accelerated motion, we are able to connect these two with a straight line, make the graph linear. Cool, like that. This time, this is the initial velocity, VI. This is the final velocity, VF. And there definitely is a change in velocity, and there's a change in time. Now, this is kind of interesting. Look, comparing these two. This one would have a positive slope. The slope is positive. It's inclined upward. The graph is increasing as you go this direction. This one has a negative slope. The graph is decreasing as you go, as time advances, as you go this direction. So a negative slope or a positive slope. That's actually really important to pay attention to. That means when you do this, when you use this formula, you could end up with a negative acceleration or a positive acceleration. That is definitely possible. What about something like this? Oh, by the way, we'll come back to the idea of positive and negative acceleration in just a moment. What about something like this? Well, if your initial velocity is some value and your final velocity is the same value, then has the velocity changed? Well, no, right? It hasn't. What is the slope of a horizontal line? Well, the slope is 0, so your acceleration would be 0 because there's actually no change in velocity. The initial and the final are equal to each other. I suppose technically this also qualifies as UAM, uniformly accelerated motion. It's really not accelerated motion. Hey, wait a minute. It's not accelerated motion, is it? It doesn't qualify as UAM. I mean, it's not, it looks smooth and continuous, but the problem is there's no change. There's no change. Nothing. That's not UAM. Silly. No. The velocity is the same value the whole time. There's no change. This qualifies as constant motion. Definitely. Definitely constant motion there. So we can see on velocity time graphs examples of uniformly accelerated motion. Oh, I didn't label this one, did I? This is also UAM. Because the change is smooth and continuous. The change is smooth and continuous. But no change. So constant motion. Cool. Well, how about non-constant motion? What might that look like? It might look like something like this. Okay. Well, I know I'm yelling at everyone, don't go dot to dot with your lines. I know. I'm not really breaking my own rule here. What I'm doing instead is simply assuming something that I've actually assumed on the other graphs as well. What I've assumed is that here, when the motion is changing, when the velocity is changing, I've assumed that the change is smooth and continuous. And same thing here, I've assumed that that change is smooth and continuous. So overall, do we have uniformly accelerated motion? The answer is no, because overall, it's not smooth and continuous changing velocity. You might say for this segment, you do have UAM, and for this segment, you do have UAM. Can you say that for the segment? The answer is no, because the velocity is not changing for that segment. Does that mean the object is standing still? Actually, no, because during that time interval, it has some non-zero velocity right here, whatever that value is. But you definitely would say there's zero acceleration here. The slope is 0. Slope of a VT graph is acceleration. Slope is 0, no acceleration, no change. So we have slope here and slope here. So in these two time segments, the velocities are changing. And what you might ask yourself is, hey, listen, these two segments, they look different. This one is steeper, and this one is not as steep. The steeper slope would indicate a larger acceleration, a larger change in velocity per unit of time. And that actually would be totally accurate. Could could you think about the average velocity for the entire time interval? Well, actually you could. What you'd want to do is something like this. You focus on the beginning and the end points of the motion on the graph, and you simply imagine connecting those points with a straight line. This new line is not actually what happens. This new line simply represents, well, if it had been UAM and it started here and ended here on the graph, well, then this line could be thought of as something you can use to find the slope. And it turns out the slope of that line would equal the average acceleration of that object. That line isn't what actually happened. The orange line is what happened, but if you wanted the overall average, you could do that. You could find the slope of that line between the beginning and the end. It does work. So, when would you use a velocity time graph compared to a position time graph? Well, what if you had knowledge of initial velocity and final velocity? If you had knowledge of initial and final velocity, well, then you definitely use a VT graph. That's totally a thing you can do. It does involve the assumption of UAM, perhaps, but that's often a safe assumption we can make. Instead, if you've got knowledge of positions and times, I mean, you also need times for this one too, but if you have knowledge of positions and times, let's do it like that, well then of course you're making a position time graph instead. Cool. One last thing I want to say, because this video's gone on long enough, I think. This equation, you have seen it before, it's already in your notes, but it is important. When does that equation work? When is it useful? Well, it works for constant motion. How do you show constant motion? On a VT graph. Well, here you go. And it works because, well, you could find the slope of that line. It's 0, but you could find it. This also works for non-constant motion. Right? I mean, we looked at that. We looked at how, for non-constant motion, you could just concern yourself with the beginning and end velocities, initial and final velocities. Imagine a line between those two and find the slope of that line. This also works for UAM, absolutely, where you have an initial velocity, a final velocity. Sometimes the initial velocity is 0, sometimes it's not. Connect them with a straight line, and that's what UAM would look like on a velocity time graph. You find the slope of that line, you've got the acceleration. It works for all three, generally, and it's really cool. There are a few other things we're going to get to, but it's going to be in a different video. There are connections, relationships between the two types of graphs. And in addition, there's something that has to be in a different video, but there is something a little extra special about velocity time graphs. Something you can learn about the motion of an object from a VT graph, but I'll have to put that in a different video. For now, thanks for watching. I'll catch you next time.